The actual edge stones, a lot of them are still there, most of them are still there, so you can definitely see the original square base, even today. How far is it around the original square base? 922 metres, exactly the same. If you take the height of the pyramid and square it, multiply it by itself, you get exactly the area of the sloping side. And lots of other amazing things, which I won't go into now. So mathematics drove them, and they were brilliant at maths. And I read this and I was fascinated. Then I read another book. And this book, Newman's World of Mathematics. Now I've moved on, I've got a 4-volume work on maths. And it's still in print, it was produced in the 50s, and it's just wonderful. And in that, I read this thing, very near the front. Of course, we think the Egyptians were rather stupid at maths. It said they were unsophisticated, that's what the book said. Because apparently, 1,000 years after they built the pyramid, they couldn't multiply. Well, not mathematically. They could do the 2 times table. They're pathetic. How will you manage? All you can do is 2 times table. They manage, I'll show you how. You, give me 2 numbers less than 20. Any 2 you like, shout them out. 12 and 18. Ooh, that's rotten. 12 and 18. Okay, thank you very much. 12 and 18. 9 and 13. 216. 12 times 18. 216. Do it in the head. But why I'm showing you this? Why did I ignore you? Because the Egyptians, if they wanted to multiply any 2 numbers, they would always, whatever the numbers were, ignore them. How can you do multiplication by that? They would ignore them. And they'd write down 1, always. Then they double it, 2. Then they double it, 4. Then they double it, 8. Oh, come on, 8. Help. 2 8s. Thank you very much. We don't need 16. We're only going up to 9. They would only do that until they covered this number, and the next one would be too big. You understand? And they stop. Then they do a little bit of maths. 2 13s. Help me. 2 26s. 2 52s, 104. And now we've got 4 numbers each side. Now the Egyptians were told there's only one way to make 9 from these numbers on the left hand side using addition. You can make every number up to 15. That's 1, that's 2. Where's 3? 2 plus 1. There's 4, 5, 4 plus 1, 6, 4 plus 2, 7, 4 plus 2 plus 1. You can make every number up to 15. So we've got to find 9. You can see it. It's sticking out. You know which 2 add up to 9. But you can do it a fail-safe way. 8 plus 4 is 12, too big. 8 plus 2 is 10, too big. 8 plus 1 is 9. When you've got your 9, you do the same to the other side. Keep this, keep that. Cross those out. Cross those out. Keep this one, keep that one. Add up the ones you kept. 13 and 4, 17 and 100. 9 times 13 equals 117. It works every single time. Now you're not applauding me, you're applauding the maths. And my book said this maths was unsophisticated. It was so off the mark you wouldn't believe. But it was the 1950s. But this is the most sophisticated thing I've ever seen. Because this was brilliant, and even a 9-year-old, 7-year-old even, with their 2 times table, can suddenly multiply numbers of any size. But it's more incredible because of today, the present day. This wonderful digital age. Let me show you. If you score the ones you used with the 1, the ones you didn't use score with a 0, you'll get 1, 0, 0, 1 reading up, and 1, 0, 0, 1 is the binary number for 9. Huh? Binary numbers. Where do we get binary numbers, kids? Tell me. In computers and calculators. Punch 9 on a calculator, up comes 9 in the window immediately. There's no 9s in the calculator. That's made up of little bars. There's no 9s. All there are in the computer, lots and lots of electronic switches to go on, off, on for 9. On, off, on. 10, on, off, 1. On, off, 8 and 2 is 10. 104 plus 26, 130. 10 times 13, 130. It's incredible. Binary numbers are unbelievably wonderful. I've got some binary cards here. They've got holes. Hole 1, hole 2, hole... Not 3. The only secret about binary numbers, to remember, it's the only secret. Remember this, when you've got binary numbers, you double up all the time. So it's hole 1, hole 2, hole 4, hole 8. With bigger numbers you need 16, 32, 64, 128, 156, 512, 1024, 2048, 4196, 96, right, and so on. Not so much now. When you buy things now, electronic gadgets, you usually have the memory you need. But a few years ago they couldn't get the memory in, and then a year or two later they could. So they used to say, get this gizmo, plug it in your camera, and you can store lots and lots more pictures. You remember that? And each one of these little chips or little plug-in things was 512 kilobytes, 1024 gigabytes, series cycles, whatever. And all they were saying is what we're doing is we're adding digits to the numbers in the memory. And you add 1 digit and you double the memory. Add 2 digits multiplied by 4. Add 3 digits multiplied by 8. Now what's happened since computers were designed and invented is every second year the memory that we can use and the speed of them increases, doubles, every second year. And that graph, is it better that way for you? That graph shows no sign of weakening. You kids are living in a technological world like an inverted pyramid. And the technology we're using is getting wider and more brilliant and more amazing year on year. So what do we want for the next mobile phones? I remember in 2002 saying, the technology's here. If your team scores a goal, Liverpool, hardly ever score a goal. But if your team scores a goal, England, right. But if your team score a goal and you've registered, it'll go bing bong, and wherever they are in the world, you press the buttons and you get a compressed video of the goal. That was ready in 2002. When it hit the marketplace, 2006, just 2007, and 2008 it started, and now it's quite regular. So the technology we're looking at. So what's the next mobile phone? Mobile phone in a watch, mobile phone in your ear, mobile phone under your skin. They're already designing them. They're already there. It's what you ask for. So you've got to be careful what you ask for the future. Because if you ask them for the wrong thing, you may be stuck with it. Alright, let me show you how these work. Hole 1 works, hole 2 doesn't, hole 4 doesn't, hole 8 does. 8 plus 1 is 9. Another one will give you, hole 1 doesn't work, 2 does, 4 doesn't, 8 does. 8 and 2 is 10. Right. 15, how long does it really take to sort them into numerical order? It would take 1, 2, 3, 4 moves. So there they are. 1, 2, 3. A bank or a building society might have 3 million customers unless they're Northern Rock. And they can sort them into account number order, alphabetical order, postcode order, and each shuffle less than half a second, several minutes. Binary numbers, they're not new. Look at this, binary numbers. Get off. A man called John Napier, a Scotsman. He said, people hate multiplying, they do. I'll help them. Here you got the natural numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Here you got the binaries, 1, 2, 4, 8, 16, 32, 64, 128, 256, doubling as they go. He says, say you want to multiply 2 numbers on the bottom of row. Say you want to multiply 4 times 8. He said, don't tell me the answer, I'll tell you. 4 times 8, above the 4 is a 2, above the 8 is 3, 2 plus 3 is 5, below the 5 is the answer, 32. So now you've seen nobody ever made a computer that can multiply. It uses coded binary numbers and simply adds them. And all a computer is thousands and thousands of cells. Each is called a half adder. and it's got 2 inputs and 1 output. So if a 0 and a 0 comes in, out goes a 0. If a 0 and 1 comes in, out goes a 1. If a 1 and a 0 comes in, out goes a 1. And if a 1 and a 1 comes in, out goes a... No. You can't have 2. No. Out comes a 0 and carry 1 to the next half adder. And that's all computers do. So never kid yourself, computers are clever. They don't know what they're doing. They don't know what they're doing. We're the clever ones. It'll always need us. But that's what I discovered. Just